This session we'll be learning about round robin scheduling algorithm. Especially this algorithm is used in multitasking operating system. What is a multitasking operating system? Whenever we see multitasking operating system means it is an extension to multi-programming. Extension to multi-programming. You know what is the meaning of multi-programming? Number of tasks can be executed parallelly. But in this case, we are going to attach a what? Time quantum. So whenever you see that multitasking operating system is nothing but multi-programming plus time quantum is multitasking operating system. So what is the idea here is whenever group of the processes are available in ready queue, whenever the group of processes are available in ready queue, and ready queue dispatches one by one jobs to CPU, which is nothing but run state. Assumption P1, P2, there are two processes are available right now in ready queue. We need to add a time quanta for them. So time quanta, I say that 2 units of time, which indicates that P1 will be executed sometime with the CPU, then afterwards P1 brought back to the ready queue, because after execution of 2 units of time, P1 has to come back to ready queue, then P2 will be dispatched. Then P2 is executed 2 units of time quanta, then it gives a chance to P1. Again, this time P2 has come. Initially P1, after that P2, while coming P1 is coming back and P2 is coming back. So that is the meaning of what? Round robin fashion. The processes are lying in between ready queue and run state unless and until their burst times are completely zero. That means completely executed. So you keep it in that mind. So let us see. There are few processes have come by name P1 and P2 and time quantum is 2. They have arrived at time 0, no doubt in that. And burst times are something like this. Its burst time is 2 and its burst time is 4. Let us take this is 3. Then what happened? Initially both the processes have come at arrival time 0. Then ready queue consisted jobs. So P1 is there and P2 is there. Now P1 is executed for how many units of time? Up to time quanta. You can't take more. Up to time quanta. Then it gives a chance to P2. Before it is giving a chance to P2, it has to fall into queue because P1 is not completed, still it needs a 1 unit of time. Then P2 right now CPU, then right now it is in ready queue. The status has changed. The context is changed. Initially the context of P1 is run state. Then right now the context of P1 is in ready state. Now P2 is executed, right now it is with CPU up to time quanta 2 units. I am talking about time quanta 2 units, don't forget this. Then it is executed for 2 units of time and balance is 2. Then P2 also joined the queue. P2 also join into the queue like this because it is not yet completed. Now the P1 which is in ready state is converted to CPU state because it is a wake up that your chance has come. So during that time P2 is in ready state. Now P1 is executed how many? Only one is needed for me. It exits though I have got 2 units of time quanta, but I don't require that much. So only I am executing 1 unit of time, then P1 is released. Then after that chance has come to P2. Then it got the chance. It executed 2 units of time. executed up to 2 units of time, that process also completed. So P1 is removed completely, P2 is removed completely. That's the meaning of round robin system. So what is the flow here? The flow is initially all the processes are in ready queue and process executes up to time quanta. We need to check if your burst time is lesser than is equal to time quanta. If your burst time is lesser than is equal to time quanta, if it is yes, execute. If it is yes, execute it, then come to terminated state. Because the process is completed, it comes to terminated state. If it is not, if your burst time is more than time quanta, if your burst time is more than time quanta, then you need to execute up to time quanta. You can't execute more than that. Execute up to time quanta. Again, we will cross check a condition. What is that? After executing up to time quanta, next rotation we will cross check. Do you completed or not? Let us check the process is completed or not. The process is completed or not. If this process is not completed, then it goes to ready queue. It goes to ready queue. If it is completed, then it goes to terminated state. So this is the idea of round robin. It is completely based on FCFS only. First come first serve. Then add it what? Time quanta. If your time quanta is too large, it looks like FCFS only. If time quanta is too less, what is it meaning of that? Let us say time quanta is only 1. P1 and P2, it requires 4, it requires 6. This is their burst time. And their arrival times are 0 only. So in the ready queue, what happened? P1 and P2, both processes are available right now. And how much time P1 should execute? Only 1 unit only. So P1 executed up to 1 unit of time. Because according to our condition, what is that? If your burst time is lesser than is equal to time quanta, if it is yes, execute and complete. If it is no, execute up to time quanta. So your burst time is a 4 and your time quanta is only 1. Therefore, P1 is executed. Let me write your Gantt chart here. P1 is executed for how many units of time? Only 1 unit of time only. It comes at 0, it executed only 1 unit of time. Balance is 3. So it checks now P1 is completed or not. It checks after executing time quanta. We will check that after executing time quanta, is it completed or not? If it is completed, it will terminate. If it is not completed, P1 has to come to queue. P1 has to come to queue, ready queue. Right now you are in ready queue. Earlier you are in CPU. This is in ready queue. Now you are swapped back to ready queue. And P2 get a chance. Now P2 is executed here. P2 is executed. It goes to CPU now. P2 is executed for again 1 unit of time. Still balance is 5. Therefore, P2 has to come to queue. Then P1 will get a chance because here right now it is P1 is executed 1 unit of time, balance is 2. Then again P1 has to come to queue. Then P2 has to execute. It executed 1 unit of time, balance is 4. Again P2 has to come to queue. P2 has to come to queue. P1 is there now. P1 is executed another 1 unit of time. Again it has to come to queue. Then after that P2 is executed, balance is 3. Then again P2 has to be in queue. See that how the queue is increasing. Now P1 is executing, it's completely executed now. P1 is executed, so remove. So that is the condition. What is the condition? After executing up to time quanta, then if it is completed, you go to terminated state. Go to terminated state. P1 is released. Now P2 is only alone. P2 is executed for 1 unit of time. Balance is 2. Again P2 is executed for 1 minute of time. And balance is 1. Again P2 is executed for 1 unit of time. Then balance is what? 0. So P2 has come how many times? 6 times it has to come. 1, 2, 3, 4, 5, 6. P1 has to come how many times? 4 times. 1, 2, 3, 4. So let us write. This is 2 and 3, 4, 5, 6, 7, 8, 9, 10. P2 completed. P2 completed at 10. P1 completed at 7. So this is what exactly the idea of a round robin. So round robin scheduling, this is the flow chart. All the process initial in ready queue, execute up to time quanta. If it is completed, make it a finish. If it is not completed, keep it in the queue once again. But what is the issue if there are multiple number of context switches happen? You observe that the process is bringing from ready queue to run state. The process is bringing from ready state to run state. The process is moved from run state to ready queue. So you see the time between two processes. This time is nothing but context switches only. Context switching time. Context switching time. What exactly the meaning of context? Context is the current status of the process. So the set of attributes of the process is your context. Right now, initially, P1 and P2 are in ready queue. And P1 is executed. P1 context is what? Run state. P2 state is what? Ready state. Then P1 is executed. Again, it is coming back. So P1 becomes what? Ready state. P2 becomes what? Run state. Likewise, if you observe that one time CPU is with one process, the other time CPU is with what? Other process. Therefore, you see that 1, 2, 3, 4, 5, 6, 7, 8, 9. These are the context switches. Whenever context switches are increased, if context switches are increased, then context switching time also increased. When context switching time is increased, then overhead is increased. Process completion time becomes what? Very. So let's see theoretical points. It is completely based on arrival time and the time quanta. It's very similar to FCFS algorithm. Don't take time quanta too slow. Don't take time quanta too low. Don't take time quanta too high. Better you take the mid portion of time quantum. Selection is also very important, whether you are taking high time quanta job or low time quanta job. So let us see some problems. What is the advantage here? Response time is increased. Context switching time due to total number of context switches. Let us see the problem. The problem is initially all the processes are in ready queue because they have arrived at time 0. P1 is there, P2. According to FCFS, I am dropping the process because it is following FCFS only. Just add a time quantity to that. The first P1 get executed at 0. P1 executed at 0 because it is right now at the ready state only, front of the queue. Then P1 is executed up to time quanta 2 units only. Balance is 2. P1 is not completed, right? Because P1 needs 2 more units, so P1 will be added to the queue. Now The front of the queue is P2. P2 is executed. P2 needs 5, but I can give only 2 according to this. 3 is the balance. P2 is not completed, right? So P2 will be added into the ready queue. Right now it is reached to 4. According to the queue, P3 is there. So P3 is executed. 6 it is needed, but I can give at a stretch 2 only. Balance is 4. So by 6 it completed. P3 is it completed? No. So P3 will come to queue. Then right now head of the queue is a P4. So P4 is executed. P4 needs 3. I can give only 2. Balance is 1 by 8. So P4 also not completed. It comes to the queue. Right now head of the queue is a P1. P1 requires how many? 2. Yes, I got completed. So P1 is executed. So you can remove that P1 from the queue. You can remove that P1 from queue. So remove P4. Now, right now, this is a P2. P2 requires how many? 3 units, but I can give only 2 units only. Balance is 1. So P2 is executed 12 units. So by 12, it is reached. P2 is not completed because still it is balanced 1. So P2 comes to the queue. Remove this. Now head of the queue is a P3. P3 requires 4, but I can give in second round also 2 only. The balance is 2. So P3 is executed, is at right now 14. So P3 will be joined the queue. Right now head of the queue is a P4. P4 is joined. It requires only 1 unit. Okay. It is completed. Plus 1. It is 15. Remove from the queue. It is completed. Now head of the queue is P2. P2 requires how many? Balance is 1. Okay, completed. So P2 is executed 16 and remove from the queue P2. No need. Then in the ready queue you are having only one process P3. So P3 is executed. P3 requires how many? 2 units. It get completed. So 18. So need not add to the queue. This is how the round robin works. First time P1 is come, then P1 is rounded. P2 has come, P2 is rounded. P3 has come, P3 is rounded. P4 has come, P4 is rounded. Once again, P2 has rounded. Once again, P3 has rounded. So their completion times. P3 is completed 18. And P1 is completed. P2 is completed. P4 is completed. You know turnaround time. Completion time minus arrival time. 10 minus 0, 16 minus 0, 18 minus 0, 15 minus 0. Wait time. Turnaround time minus how much time you spent with the CPU. So 10 minus 4, 16 minus 5, 18 minus 6, 15 minus 3. Balance is 6. Balance is 11. Balance is 12. Balance is 12. So average turnaround time divided by 4. Average waiting time divided by 4. So 26, 34, 44, 49 by 4. This is 17, 29, 39, 41 by 4. Okay. Let us see one more problem. At arrival time 0, only one process came, P1. Now at 0, P1 is executed. What is the time quantum given? You will get in exam. Time quantum 2 is given. It executed 2 units. Now let us verify clearly. During execution P1 up to 2 time units, 2 more processes have come. P2 has joined, P3 also joined. Remember, during execution of P1, 2 more processes have joined. Then 2 you need to drop into the ready queue. Now you check P1 is completed or not. It's not completed. Therefore, P1 will add it to the queue. This is the head. This is the head now. Now P2 is executed up to time count. I need 5. I can give only 2. Balance is 3. Now it executed up to 4. During execution up to 4, two other processes have come by name P4 and P5. Now you see P2 is completed or not. First drop into the queue, then bring that old process to ready queue. P2 has not completed, still 3 more is needed. So P2 will join into the queue. Now right now ahead of the queue is P3. P3 is executed. P3 need to successfully, you can finish this. P3 is completed by 6. So remove the P3 from the queue. It won't join into the queue. Now during execution of this process, one more process also come, nothing but 6. Right. Now head of the queue is P1. Now P1 executed. How many? 2 units needed. Okay. Successfully executed. Remove from the queue P1. Now all the processes have come, right? So there is no need to check every time whether the process is brought to the ready queue or not. Now the next process is P4. So P4 needed only 1. Make it finish. I can give up to 2. You're asking me only 1. So remove. 3 process completed right now. So P4 asking only 1. I executed plus 1 and 9 it becomes. It is completed. Now head of the queue is P5. P5 is requiring how many? 6. I can give only 2. Balance is 4. And P5 is joined the queue because all the process have brought into the queue. Then 11. Then head of the queue is P2. P2 is required 3. I can give only 2. Balance is 1. So P2 is executed 2 units. So P2 joined into the queue once again. Now head of the queue. What is the head of the queue? P6. P6 is requiring 3. I can give only 2. So balance is 1. So P6 has brought 15. Now P6 will be into the queue. Now head of the queue is P5. P5 need balance is 4, but I can give only 2. Balance is 2. So P5 is executed 2 more units. P5 again brought to the queue. Then head is a P2. P2, how many you're asking? Only 1. Balance is 0. So 1 unit you execute. 18. Remove from the queue. And this one. This is P6, right? Small chain is P6. Now head of the queue is a P6. So P6 is executing. Balance is 1. So execute completely P6. It's also completed. And only one process left, that is a P5. P5 is executed 2 units of time. So 21. That's it. Each process how many times come? Let us check. P1 has come only 2 times. P1 has come 2 times because it needed 4. P2 has come how many times? 2 plus 2 plus 1. 3 times it has to come. P2 and P2 and P2. P3 only 1 time because it need only 2 units. P4 only 1 time because it needed only 1. P5 6 units. 3 times it has to come. P5 and P5 and P5. P6 how many? 3. So 2 times it has to come. P6, 6. So their completion time, P5 completion time is 21, P6 completion time is 19, and P2 completion time is 18, and P1 completion time is 8, P3 and P4. P3 completion time is 6, and P4 completion time is 9. The rest you know. So P2 is at 18, P6 is at 19, P5 is at 21, and P1 is at 8, and P2 is at 8. So this is how to do round robin system which is following FCFS with the time quanta. What is the condition I said? Check the arrival time of the process. If only one process is there, drop that process, execute it, and during that execution you cross check any other process have come or not, because they may not available in ready queue. If they are, drop it. Then check this, the previous process is completed or not. If it is completed, remove from the queue. If it is not completed, add it at the tail of the queue. So that is about a round robin. You know turnaround time, completion time minus arrival time. So 8 minus 0, 18 minus 1, 6 minus 2, 9 minus 3, 21 minus 4, 19 minus 5. This is 8, this is 17, this is 4, this is 6, this is 17, 14. Waiting time 8 minus 4, 17 minus 5, 4 minus 2, 6 minus 1, 17 minus 6, 14 minus 3. You take the average of it.